Yeah, greetings all. This video we're gonna talk about projection, or which you can also refer to as motion under gravity. Projection is an object or particle or body which moves through space on projection. You see, and this projection is highly influenced by gravity. You see, because gravity varies from place to place. So gravity influence and affects the a projected motion. So any object or body or particle which is being projected, you see, is highly influenced by gravity. And gravity varies from one place to the next. You see, like some of the factors or the reasons why gravity vary from one place to another. One of the factors simply mean the earth is not a perfect sphere. That's one of the factors. And the second reason again why gravity varies from place to place, you see, the altitude of a place. That's another factor. The altitude of a place also makes gravity to vary from one place to another. And the second factor again that makes gravity varies from one place to another, like the rotation of the earth on its axis. This again another reason why gravity varies from place to place. And the other reason again that makes the earth to vary from one place to place, the magnitude of the force. So these are some of the reasons why gravity varies from one place to the next. You see, like let's give an example of this gravity. Like the gravity on earth, it ranges. Like the gravity on earth ranges from 9.81 meters per second square to 10 meters per second square. If we consider the gravity on the moon we have it to be 1.625 meters per second square. We also have the gravity on Mars, which is to be 3.7712 meters per second square. So these are some gravities in different places. You see, on the earth, maybe we can consider again the Jupiter, Mars, the moon, and other places. So gravity varies from place to place. So gravity has high influence on a projected object or body or particle. So these are things we have to take note of. So under this video, we are going to consider projection. And under projection, we consider how an object is projected vertically. What are the equations or formulas we are going to use to solve basic problems? When an object is projected horizontally, what are the formulas or equations we are going to use to solve basic problem? And when an object is projected in an inclined form, which you can also refer to as projectile. So these are some of the things we are going to consider under this video. So considering this video, we have to consider the equations of motion. Let's take equations of motion. If we consider equations equations of motion. So the equations of motion we are going to consider, the first one, we have v equals to u plus or minus gt. We also have v square equals to u square plus or minus 2gh. We also have s equals to u plus half gt square. These are some of the formulas or the equations we are going to consider. So considering this, if we start from the three projections, like projection, we are going to consider the first one, the vertical projection. We will also consider the horizontal projection. We also consider the incline or projectile. So if we consider the first type, vertical projection, vertical projection. So what are the formulas we may use when solving equations or problems relating to vertical projection? You see, so let's start. Let's say if an object or body or particle is projected vertically, let's say this is the trajectory in which the object takes. The trajectory will project an object. This is the trajectory in which the object takes or the path. So if we project an object, it will never move forever. It must reach its highest peak. When the object reaches that highest peak, you see, that point we can consider certain things. Let's say the object reaches at this point. What are the things we are going to consider? So therefore, the distance or the height automatically becomes h max when it reaches at this highest point. When s becomes h max, we need to consider that the vertical velocity or the final velocity v automatically becomes 0. And we also have to know that since the object has not yet attained its maximum height, but the object is still moving, let's say it stops at this point, we have to take note of that. We have to take note that this s distance will still become distance because s will never be h max because it has not yet attained at its highest point. But when it attains its highest point, this total distance s becomes h max. You see. Another point again we need to consider when an object is projected vertically, simply the acceleration due to gravity or simply the acceleration of free fall becomes negative g. Because when it moves vertically upwards, gravity becomes negative. When the object is coming or is falling down, gravity, the A becomes negative. So these are some of the things we need to take note of. So how can we use this to derive equations we are going to use to solve problems under this? We take the first equation. We say V equals U plus AT. If we take this equation from simply the equations of motion, V equals to U plus AT, you know, when an object reaches its maximum height, the moment an object reaches its maximum height, V becomes 0. So this V will be 0 equals U plus, since the object is being projected vertically, this A automatically becomes negative G and T. So if we further simplified, we have 0 equals U minus GT. If we transpose, we have GT equals to U. We make T the subject, T equals to U all over G. This is one equation. We consider it to be equation 1. You see. So this equation is one of the formulas we are going to use to solve any problem that has to do with an object which is projected vertically. And this T, it refers to the time an object reaches its maximum height. The time taken for an object to reach its maximum height is what we refer to as this small t. And this G, we all know it will be the gravity, the free fall. And this U is the initial speed, or we can also call it as the speed of projection. You see, that's the second point. We also have another term which we'll consider as time of flight, which is big T. Time of flight is the time taken an object to be in the air. If you project an object, the time taken an object to be in projection is what we refer to as time of flight. And this time of flight is twice the time taken an object to reach its maximum height. So which can say time of flight T is going to be 2T. So T equals to 2 times, this T is, we have it to be U all over G, which you can also say 2U all over G. We can call this to be equation 2. So when you have a question relating to vertical projection and you are required to calculate the time of flight, where the initial speed is given or the speed of projection is given and the gravity is given or not given, hence on Earth you can take 9.81 meters per second square, or you can as well take as 10. So U is the speed of projection and G is the gravity. So T now equals to TU all over G. But if the question specifies that an object is projected on the moon, you have to know the gravity on the moon. If an object is projected on Mars, you have to know the gravity on Mars, and so on. So this time of flight T is 2U all over G. These are some of the quantities you might be asked to find. The other quantity we'll be asked to find is the H max, which is the maximum height. So the maximum height, we can have it from the second equation, this. If we consider this equation, V squared equals U squared plus 2AS. As we all know, when an object is projected vertically, V is 0, so we have 0 squared equals U squared plus 2 into, what is our A? Our A here is negative G because the object is projected vertically, and our S here is H max because it reaches its highest point, so we have H max. So if we simplify, 0 equals to U squared plus times minus 2G H max. So if we make H max the subject, we have H max equals to U squared all over 2G. This gives us equation 3. So for any vertical projections, mostly these are the things you might be asked to calculate under this level. the time an object takes to reach its maximum height, and the time of flight, and as well as the maximum height. This is so all about vertical motion for this level. Is these are the quantities we might be asked to calculate. So after capturing this, so the next point we also move to horizontal projection. If we consider horizontal projection, or consider horizontal projection. So if we consider horizontal projection, we take from the equations of motion, we take this equation S equals ut plus half gt square. You see, let's say an object is being projected horizontally. Let's say it's placed on an object on an height. So the distance, this is the height of the object, and this distance is what we call the horizontal range R. You see, so in this case, what's going to be our R and what's going to be our H? So our R here will term it to be this, which is the horizontal range, and this quantity will term it our H. So let's see what would be the next case. So this implies our R here, the range, which we refer to as the horizontal range. Horizontal range R is equals to UT. Let's say this is equation 3, this map to equation 4. And we also have our vertical height, which we refer vertical height. This is the vertical height, H. Vertical height, H, we have it to be half gt square. We can mark this as equation 5. You see, but this equation can as well be simplified, because if this H is equals to half gt squared, if we make t the subject here, is going to be the square root of 2h all over g, which can also give us as equation 6 if we make t the subject here. So since we make t the subject here, what will be the range now? So this range R now becomes ut, but what is u? If we don't know, and t is this, so which also referred to as 2h all over g. This gives us equation 7. Let's see. So these are some of the formulas we may use to calculate the range of projection for under the horizontal projection. We can as well require to calculate the time, or sometimes you might be asked to calculate the vertical height. You might be asked to calculate the vertical height, or you might be asked to calculate the horizontal distance, which we also refer to as range, because the range is just the horizontal distance from the point of projection to the point where the object reaches its projection plane. The horizontal range simply means like those is simply defined as simply the point of projection to the point where the object reaches its projection plane. So these are some of the derivations or the formulas we use to calculate the range R, the vertical height H, and the time of projection T under the horizontal projections. So we completed 2 projections, the vertical and the horizontal. If we consider again the third type, which is the inclined projection, if we consider the third type, inclined projection. So if we consider inclined projection, if we consider inclined projection, so what are the things we consider there? An inclined projection, we can also call it as projectile. You see, it's the same thing when it's just as any object or body that moves through space on projection. Projectile simply means any object or a body or a particle that moves through space on projection is what referred to as projectile, which you can also refer to it as projection motion. We have to take note of this. An example of projection or projectile, like throwing or kicking a football, throwing stone, like short put, you see, and long jump and high jump. These are all basic way of defining projection practically. You see, so in function, like there are certain things like short put. You can also consider an example of short put, volleyball, you see, basketball. These are all an examples of projectile, you see. Now, there are certain things which we cannot consider as projectile. If I have this marker, if I try to project it, it has a velocity, and this velocity we call it to be the speed of projection, or the initial velocity. So in this case, when the object reaches its maximum point, we can know that v is 0, and u is going to be the speed of projection, which will be a certain value. But in another words, like say if an ant or a fly, or let's say, and let's consider an air flight or a rocket, you see, or an airplane. Can we consider an airplane, the taking off of an airplane, can we consider that to be a projectile? Or when an airplane is moving, can we consider that to be a projectile? You see, does an airplane considered to be a projectile? An airplane cannot be considered to be a projectile. Why? Let's consider, before we reach to the answer, let's consider a short put. If I throw this marker, the speed of projection in which is going to be the same is going to be uniform. You see, and it is affected, this marker or the short put or whatever thing that is being thrown, like a stone or calculator or object which is being thrown or which is being moved through projection, you see, it has an initial speed. And this initial speed and this object is being influenced and affected by gravity. But can gravity really being affected to the air flight? You see, so why an airplane is not considered as a projectile? The reason, because airplane does not move with a uniform speed. That's the first point. And the second point is does not influence or affected greatly by gravity. So those are the two things, the two keywords. Why airplane or air flight, not airplane or air flight. We can also consider these flies, these ants, these bats. So you see, all of those are not considered to be projectile when they are moving or when they are in motion, because their speeds vary. They don't have constant speed. Their speed varies. That's the first reason. And the second point reason again, they are not greatly affected by gravity. So if you come across such questions, why bats, why ants, why insects, or anything that flies, or let's say an airplane or rocket, why they are not considered to be a projectile? Because they are not influenced by gravity. And the next point, they do not move with a uniform speed, because their speed or velocity varies as they proceed. So this is just a basic point. So under inclined projection, we are going to derive from formulas we are going to use to solve projection, which is influenced by incline. So let's consider the diagram. Let's say an object is being thrown. Let's say I have this vertical projection, also have this horizontal projection. This object is being thrown and it is moving. It stops at this point. So this is the speed of projection. So since we have this to be the speed of projection, this is u, and this is the angle of projection. Let's call it to be theta. And we have, this is the vertical speed, and we have, this is the horizontal speed, which is ux. You see? And this angle here, let's call it to be beta. And beta here is 90 minus theta, because this angle is 90. You have to take note of this. This is 0, 0, the axis. So when the object is being thrown, when it reaches its max, this is the maximum point or the maximum height. So we have h max. We are in s here is equal to h max. This. So we also have to consider the horizontal distance in which the object moves. You see, these are, we call it to be the horizontal distance or the horizontal range. The horizontal distance of the horizontal range is just the distance it takes from the point of projection to the point where the projection reaches its projection plane, where it reaches this point. And maximum height is the height an object takes to reach its highest peak. You see, and the angle of projection is just the inclined value wherein an object is being projected. If we consider this projection, we're trying to derive formulas we are going to use to solve problems under projectile. Now, the things we are going to do, let's resolute this diagram. If we drop a vertical line here, it's going to give us an angle of 90. So let's extract this diagram. This line, we have a triangle here. If we extract that, we have this diagram to be in this form. This is 90 and this is theta. And this is the speed of projection. We have it to be u. And we assume this is the vertical projection, call it to be uy. And this is horizontal. Since here is ux, we call it to be ux. You see, this is ux. So what's next again? We can use this guy, SOHCAHTOA, to find. This S is sine. Sine theta, if we take sine theta in this case, is going to be O all over H. So sine theta, the O is Uy, all over the H is U. So therefore, Uy is going to be U sine theta. Similarly, Ux, since Uy is sine, so Ux is going to be cos, U cos theta. So we have these values. So having these values, so what's going to be the next step? So if we move now, we consider, let me just clear this. We consider the equations of motion. If we consider the first equation of motion, so we say we have V to be equals to U plus AT. And for vertical projection, when the object reaches at this point, the same thing, V is 0. So V will be 0 equals to U is the speed of projection. And A, since projected vertically, A is negative, and T is this, you see. So U now equals to this U is going to be Uy. But what is Uy? Uy is U sine theta. We have it to be U sine theta minus GT. So if we transpose GT equals to U sine theta, if we make T, so T equals to U sine theta all over G. We have equation 7, so this will give us equation 8. You see. So for inclined projection, anytime you come across an object is projected in an inclined form, just know that the time the object takes to reach its maximum height can be simplified as U sine theta all over G. And similarly, for the time of flight, which is T, is twice the time taken to reach its maximum height, which can be simplified as 2U sine theta all over G. This gives us equation 9. You see? So having this, we also need to consider the horizontal range. How can we consider the horizontal range? The distance from this point to this point. Because the object is being projected from this point, it moves. Because here the distance is the same, it moves and it drops to this point. Yeah. There's another point again we also need to consider. Like I was saying, why an airplane is not considered to be a projectile? Because two main facts. Because the airplane has a varied speed, right? Its speed of velocity varies. And the second point again, because it's not greatly affected by gravity. So those are the two reasons. Now, we need to take note of the vertical speed on the horizontal speed. Why the horizontal speed of a projection remain the same at every point of its flight? We need to take note of this. This might be another simple way. The horizontal component of a projection, right? Like the horizontal speed or component of a projection always remains the same. If this velocity is 10 meters per second, at this point it's 10 meters per second, 10 meters, 10 meters, 10 meters, 10 meters, throughout. So the horizontal velocity or the horizontal component of a projection always is the same. You see? So we have to take note of that. Ux is always the same, but Uy keeps changes. Either it becomes 0, because at this point, we can see that at this point, the vertical velocity will decrease. At this point, the vertical velocity will remain constant, while at this point, or it becomes zero. And at this point, the vertical velocity will increases. We'll come to that. I will explain something which relates to this point. So we have these two equations for incline 1 and 2, which is 8 and 9. If we also need to find the range, and we also need to find the maximum height. So these are the two things that remains. So if we want to find the range are the horizontal range. We can also call it as the horizontal distance. You can either call it horizontal range or horizontal distance r equals to from the vertical projection, we have u equals to ut plus half gt square. We are to consider this to be the range. We r equals to ut. We can also use it here at this point. So r equals to u, but this u now is, since it's horizontal, we consider its p to be the horizontal component, which is ux, and we also consider the time we calculate, because the projection starts at this point and it ends at this point. So this is the total time. The total time taken from this point to this point is the big T, which is referred to as time of flight. So consider it to be this. So this range is going to be, what is ux? We have it to be u cos theta times, what's the t? And t is given as 2u sine theta all over g. This is it. So if we simplify this value, so we have the range to be u times u is u square times 2 sine theta cos theta all over g. But 2 sine theta cos theta all over g, 2 sine theta cos theta is 2 sine 2 theta. This is going to be u square. This whole value is going to be sine 2 theta divided by g. So this is equation 10. So if we are asked to calculate the range, the horizontal range of an inclined projectile is given as u square sine 2 theta all over g. We have to take note of this. So there is, in under horizontal range, we have to take three main cases which are very, very sensitive. Let's discuss this. Let's see what we need. In under horizontal range, some of the things we might also be asked to find. You might be asked to find the maximum range. So how can we have the maximum range? So let's write, since we have the horizontal range to be u square sine 2 theta all over g, what about the maximum range? Maximum range simply means when the angle of inclination reaches at a particular peak. And what is that maximum range? What is that angle it reaches? So to find the maximum range, there is a condition. Let's say for maximum range, for R max, for maximum range, we have to be, this angle is considered sine 2 theta will be equals to 1. And if we are looking for theta, we'll say 2 theta is going to be sine inverse of 1, and 2 theta, sine inverse of 1, if you use your calculator, is going to be 90 degrees. You see, in terms of radians, it's going to be pi all over 2 radians. So if we divide both sides, theta is going to be 90. If we divide by 2, it's going to be 90 divided by 2, which is 45 degrees. But in terms of radians, it's going to be pi all over 4. We have to take note of this. You see? So having this now, it looks like this. So this range, this projection, that means this angle here is 45 degrees, here again is 45 degrees. So therefore, this value becomes R max. This is the maximum range. It becomes R max. Wherein this is U, and this is uy, and this is ux. So this angle becomes 45, 45. So at maximum range, therefore, theta here becomes 45 degrees. We have to take note of this. At maximum range, the angle of inclination automatically becomes 45 degrees at this point. So we have this to be ux for the horizontal component and uy for the vertical component. So we have to take note of this. I think this is just the relation for the horizontal range. So having this, the next point we also consider So we also consider the last equation, which we refer to as the maximum height bridge. If we consider the maximum height bridge, you see, we also need to consider one of the equations of motion. If you consider one of the equations of motion, let's consider. So one of the equations we say from v squared equals to u squared plus 2as. We need to consider this. So v for vertical projection, v is v0 square equals to u square for vertical. This is going to be ui plus 2a will be negative g, and s becomes h max. This is just this. So 0 equals, but ui, we have it to be u sine theta all squared plus times minus 2g h max. So if we expand this, this is going to be u square sine square theta minus 2g h max. We have to take note of this. So if we continue, we transpose, this is going to be 2g h max equals to u square sine square theta. We divide both sides, so we have h max equals to u square sine square 2 theta square u square sine square theta all over 2g. This gives us equation 11. So these 11 equations for basic under motion under gravity, or for basic for projection, with these 11 questions, with these 11 equations, you can solve any problem relating under projection, being it vertical projection, horizontal projection, or inclined projection. So you'll be able to solve problems under this. You see. And I just remember here at this point, before we come here, at this point, this maximum, since theta is 45, if we slot theta 45 here, that means this r automatically becomes r max. It's going to be u squared times sine, because if theta is 45, 2 times 45 is 90 all over g. Sine 90 is 1, so at maximum range, u square, you have to take note of u square is also g. So this is going to be equation 10, no, equation 11. So this will be equation 12. You have to take note of this, because there are certain times you'll be asked to calculate the maximum range. So you should be able to remember the maximum range is just u square over g. Or certain times you'll be asked to calculate what is the g in terms of maximum range. So g in terms of maximum range, when you make g the subject, so g will just be u square all over r max. So these are some of the things we need to consider. Let's see. So these are the equations we need to consider. So you have to take your time, you go through the video, you go through the slides, and you also go through the steps involved for you to know how these equations are derived carefully. Take note of that. So now, after this, we need to move to problems. Let's see if we can able to solve 3 or 4 problems. So we take the first problem. So the first problem, it reads, a missile is projected with a velocity of 250 meters per second at an angle of theta to the vertical. You see, if the total time of the missile is 25 seconds, so calculate the value of theta given the diagram. So we have the vertical speed, the horizontal component of the speed, and we are given the speed of, because this U represents the speed of projection, or is the initial speed, you see. So we are required to calculate the angle of inclination theta. We need to calculate this theta, the value of theta, the angle of theta. So to also find the value of theta, but we have to take note of certain keywords. We are given the initial speed u, which is this. We are also given the time of the, if the total time, this is the total time. The total time of the flight is similar to the time taken from this point to this point. The time the object takes projected, the time when the object was projected from this point, it travels to this here, the total time. And this total time definitely is the big T, which is the time of flight. You see, so the time of flight is given at 25, and we are given the speed of projection, you see, or the initial speed to be 250, and we we are required to find theta. So all what we need to know here, we just need to know the value of t. We just need to know the formula of t. If we know the relation of t with respect to u and theta, we can easily find the value of theta. But mind you, the angle of projection is for this diagram is not theta. The angle of projection is this. We need to find this angle of projection. Let's say this angle of projection is given as beta. So if we need to find theta, so in this case, theta is going to be 90 minus beta. We need to find this beta. These are things we need to take note of. So if we find beta first, if beta is 10, so theta is going to be 90 minus 10. If beta is 15, theta is going to be 90 minus 15. If beta is 20, theta is going to be 90 minus 20, and so on. So we need first to find beta. That value, we'll slot it here. We carefully find the angle of theta here. Because the angle of projection is this, not outside. So we need to take note of this. So we need to know the formula for time of flight. If we consider the formula for the time of flight, we say time of flight, which is big T, if we have it to be 2u sine theta all over. This is the formula. And we are given the time of flight to be 25 seconds. Put it 25 equals to, and we are given the initial speed u to be 250. So we have 2 times 250 sine. In this case, theta, we are looking for beta. Let's say sine beta all over g. We can take this to be 10. You see, so we can say this 0 cancels 0. So we have 25 equals to 2 times, going to be 50 sine beta. We'll divide both sides. So sine beta is going to be 25 all over 50 as this. So beta now is going to be sine inverse of 25 divided by 50 is going to be 0.5. So sine inverse of 0.5 will just be something like 30 degrees. Yeah. Sine inverse of 0.5. Yeah, it's 30 degrees. So theta. But now we are required to find the angle of theta. We say angle of theta here is just going to be 90 minus beta, which is 90 minus beta. So theta is going to be 90 minus 30 degrees. So this is going 90 minus 30 is going to be 60 degrees. But here, this you can convert it again to radians. You see, if you convert it to radians, it's just like 30 degrees times pi all over 180. 0 cancels 0, so it's just going to be pi all over 6. So suppose you are required to convert the angle to radians. So theta here is going to be 60 degrees. You see, 60 degrees, because this sine here is going to be 30 degrees, or for the first quadrant, for the second quadrant again, because if you subtract 180 minus 30, it's going to be 150, it can as well be 150 degrees. So you can consider either of the angles, but for this case, we can just consider 30, so 90 minus 30 give us 60 degrees. So this is just the basic way how we can solve problems under projectile. I hope if you carefully take your time to go through this video, by the end of this video, you will understand the whole of projection. Let's try the second example. So we continue. We consider example 2 again. And example 2 reads, two bodies, X and Y, are projected. Two bodies, X and Y, are projected on the horizontal plane with the same initial speed, both at angles of 30 degrees and 60 degrees, like respectively to the horizontal. Neglecting air resistance, calculate the ratio of the range of X to that of Y. So we are required to calculate the range of X to that of Y. You see, we are required to calculate the range of X to that of Y. So we are required to calculate the range of X to that of Y. So we need to calculate, I think we need to calculate the range for X, we'll calculate the range for Y, and the same point again, we'll find the ratio. Because the point here, we are required to find the ratio. This is the key word, the ratio of X to that of Y. That means going to the ratio of X is to the ratio of Y. Y is going to be the first value for X, Y is going to be the first value of Y. So we need to carefully take our time, we'll find the range of X the same as carefully take our time, we find the range of y. So having the two ranges, we can able to work them in ratio form and have the value we are required to find. Now, moving forward, we have these two bodies, x and y, body x and body y, are projected on a plane and with the same speed. That means the speed for x remains the same to that of the speed for y. So the two bodies have the same speed, but with different angles. That means x is 30 degrees and the second angle is 60 degrees for y. You see, this is very simple and straightforward. But what we have to know is we have to know the formula for the range of a projectile. So when you see a question, you should be able to predict, is this question related to vertical projection? Does it related to horizontal projection, or does it related to inclined projection? Since we are given an angle, definitely we can consider this to be an inclined projection. So being it an inclined projection, we have to know the formula of the range. So for an inclined projection, we have the range, the horizontal range R to be u square sine 2 theta all over g. This is the formula. You see, but we are given, we need to start for x. So say for x. For x, what is the range for x? The speed, mind you, the speed is the same. So this gonna be u square sine 2 times, what is theta for x? The first theta for x is 30, which lot is 30 divided by g. We don't know it, we can leave it like that. So therefore, Rx will be u square sine 2 times 30 is 60 divided by g. So you see, we say Rx is going to be sine 60. Let's say, what is sine 60? What do we have? Sine 60. Sine 60 is root 3 all over 2. So this will be u square times root 3 all over 2 all over g. So in simple form, it's going to be u square root 3 all over 2g. Let's say this is equation 1 for x. We'll say again for y. So ry is the same thing, u square sine 2 times, what is theta? And theta for y is 60. When slotted, 60 divided by g. So ry is going to be u square sine 2 times 60 is 120 all over g. So it's going to be u square times, what is sine 120? Sine 120 will be like root 3 all over 2. It's the same thing. This is going to be root 3 all over 2 all over g. So if we simplify that, it's going to be u square root 3 all over g, all over 2g, all over 2g. This will be 2g. So this gives us equation 2. So we have the ranges for the two. We have range x to be u square root all over 2g, and range y to be u square root all over 2g. So, but the question says, what is the ratio? So the ratio now, Rx is to Ry, is going to be, Rx is this, which is u square root 3 all over 2g, is to, like, divided by Ry is just going to be u square root 3 all over 2g. So therefore, Rx is to Ry. Find out that this will cancel because if we reciprocate it, so it's going to be Rx all over Ry. Let me just complete it here because this has already been solved. So the ratio of Rx is to Ry. Rx will maintain it to be u square root 3 all over 2 times, if we reciprocate, 2g will move up and u square root 3 will move down. Everything will cancel. This cancel this, this cancel this. So therefore, Rx is to Ry is just going to be 1 upon 1, which can as well be written as Rx super y equals to 1:1. So this is the ratio for this range. I think this is the second problem. Yeah. So we move to the third problem, the third example. If we move to the third example, let's say. So we continue with the third problem, and the third problem reads, in In his first attempt, a long jumper took off from the springboard with a speed of 8 meters per second at an angle of 30 degrees to the horizontal. He makes a second attempt with the same speed at 45 degrees to the horizontal. Now, given that the expression for the horizontal range of a projectile is u square sine 2 theta, where all the symbols have their usual meanings, show that he gains a distance of 0.8574 in his second attempt. You see. So this is a very practical question. You see. There are two cases. This long jumper first have the first target, and later you also have another second target. Let's say this is the starting point, that's the ending point. So this guy first took off for the first attempt, and it gains a horizontal range. Let's say this is the first horizontal range. There's the final point. It took off from this point, and he made again another attempt again from the starting point. This is the second point. So the range here is R2. This is the first attempt. This is the guy. This guy took off from this point. He moved from this point. He took off. He jumped from here. He made a distance of R1. He also made for the second attempt. He moved from this place and he landed at this point. He also made another distance of R2. What is the distance he gains? Because he gains a distance of this. We are required to show that he gained that is the distance, the remaining distance for the difference between the first distance and the second distance is what is given as 0.8574. You see, this is the distance he gains, 0.8574. We are required to show that the distance he gained on this second attempt is 0.8574. You see, that means we need to find the first distance, R1. We also find the second distance, R2. So this second distance, R2, minus the first distance, R1, is going to give us this. This is what exactly the question is trying to say. You see. So before we find the first distance and the second distance, we need to know the formula. And we are given the expression in which we are going to use. So carefully, we are given R1. So say first attempt, we take it as first attempt. So say R1 equals to u square sine 2 theta over g. What is u? So the first attempt, in this first attempt, a long jumper took off from the springboard with a speed. So the first speed is 8, and the angle given is 30. So we substitute them here. So it's going to be u is 8, which is 8 square times sine 2 times theta is 30 all over g. G is not given. We can say 9.81 or 10. So this is 30. So 8 square is 64. We say 64 sine 2 times 30 is 60 divided by 10. And we have the distance to be 5.542563. We can stop here. 63, or can write everything. Let's write 62584. You see, this is the distance is gained in meters here. In meters. So the second distance again, R2, is the same thing, u square sine 2 theta over g. We can write this u square sine 2 theta over g. And in this second attempt again, it makes a second attempt with a speed, with the same speed. So the speed is the same. If the speed is the same, that means this 8 is going to be 8 square times sine 2 times, what is theta? And theta is 45 degrees. You see? 45 degrees, 2 times 45, divided by g, which is 10. So his second attempt is going to be 8 square is 64. 64 sine 2 times 45 is 90. Divided by 10, so we have 6.4 meters. This is what we have. You see. So this first attempt for the first guy from here to here, I made a distance of 5.54 dash. And the second attempt again, I made a distance of 6.4. The question says, where all the symbols have their usual meaning, show that again that we are required to show that if we subtract this guy The distance he covered minus this second distance will give us this. So the distance he gains now, distance gain, the man's gain, let's say distance gain will be R2 minus R1. So R2 is 6.4 meters minus R1 is 5.542562584. So this distance, when we subtract the two, 6.4 minus 5.542562584. So the distance is 0.875437416. So approximately we can just leave it. So the distance this man gains, so distance gains is going to be 0.8754 in 4 decimal places. So this is the distance gains for this. Let's see. So I think there's a point. So we have solved 3 problems. So we move to the 4th problem. So we take the 4th problem. The 4th problem again, it says a missile is projected so as to attain its maximum range. We are required to calculate the maximum height, right? We are required to calculate the maximum height attained if the initial velocity of projection is given as 200 meters per second. And we are given the gravity of free fall to be 10 meters per second square. So this question is very simple and straightforward, but we have to take note of keywords. A missile is projected so as to attain its maximum range. I think we've discussed something on maximum range. You see, for maximum range, we say R max. What are the conditions for R max? We need to know that R max, the angle of projection is what? 45. We derive it from under inclined projection. For R max, we need to know that the angle is 45 degrees. This should be well considered. So for R max, the theta is 45 degrees. So a missile is projected so as to attain its maximum range. So at maximum range, theta is 45. Because when the missile tries to reach its maximum range, theta automatically becomes 45 degrees. Now, we are required to calculate the maximum height. So we need this maximum height. And we are given the speed of projection to be this. So since we are given the maximum height, what's the formula? So H max, we have it to be U square sine square theta all over 2g. This is the formula. I think this is it. So we are required to find H max. The moment you know this concept, you're able to find this. So it's very simple and straightforward. So since we have at maximum range, theta is 45, what is the maximum height? We'll slot what is given and we'll find our maximum height. So if we do, so we have something H max becomes, what is U is 200, so this will be 200 square times sine theta is 45 all square divided by 2, and the gravity of free fall is given as 10. So maximum height is going to be, so we can multiply everything to have the value. We say 200 square times sine 90 squared divided by 20. So we have 2000. So the maximum height is 2000 meters. This question is very simple and straightforward. So this is the 4th. So we take the last question. get A. So we take the last question, and the last question says the diagram below shows the trajectory of a projectile. You see, trajectory of a projectile. This is u, and we are given the vertical velocity, the vertical component for the velocity, and horizontal component of the velocity. We are given the angle of projection theta. We are given 3 points A, B, and C. So, and the coordinates start at both 0, 0, neglecting friction. So how does the Roman 1 says the horizontal component ux of the initial velocity u changes at the point A, B, and C. And also the second point say vertical component uy of the initial velocity u changes at points A, B, and C. So we are required to show how ux changes at points A, B, and C, how uy changes at points A, B, and C. This is all what we are required to show. So, but we have to take note of this. You have to take note of something here. Like I was saying, the horizontal component ux for this case is always going to be constant. The horizontal component of the velocity always constant. The velocity here at these levels is always constant. Why the velocity at this point is always constant? Because this is not, the horizontal component of velocity does not influence by gravity. If I throw this marker, there is force of gravity that influences it. Gravity affects an object which is being projected. But if I kick a ball horizontally, gravity is not affecting objects which move in the horizontal position. Since it's not influenced by gravity, so therefore, ux becomes constant. Because if I throw this marker vertical upwards, you can find out that gravity forced the marker to move downwards again. But if you kicked a ball, you see, forward, the gravity will not be able to make that ball to bounce backward again, unless it reaches an object which might make it again to bounce backward. But hence there is no object or friction that tends to stop it, it will continue to move. You see, so gravity does not affect horizontal component. That's the reason Ux becomes constant at the horizontal position. So now the question says, for us to neglect friction, how does the horizontal component Ux affect point A, point B, point C? And how does the vertical component Uy, that the vertical Uy, affect point A, point B, and point C? This is what the question is trying to say. So, if we simplify this, we can make it, we say Roman 1, we say at point A, what's going to be Ux? As I was saying, Ux is constant. Nothing changes. Ux is constant. And what is Uy? Uy at this point will, let's consider the relation, the range. Because we have the range, because we have to consider the distance, the range. The range here will decrease. This is the range for the first one. If you consider this distance. If you come here, this is the range for the second one. And if you come here at C, this is range for the third. So at this range, you find out that this range, second and third, is greater than this first one. So at this point, this velocity, because range is u square sine 2 theta over g. Range is directly proportional to theta, is also proportional to the speed. If the speed decreases, the range will decrease. If the range decreases, the speed will decrease. So at point A, the range is smaller. Therefore, the speed is going to be smaller. So Ux will decrease. Therefore, it will decrease. This is the second point. So we take to point B. At point B, as I was saying, Ux is always constant. So Ux here is constant. And Uy, at this is the maximum point you have to take note of. At maximum point, the velocity is 0. So if the velocity is 0, therefore the range will be 0. So therefore, Uy is going to be 0. We have to take note of that. You see? If we move again at point C, the same thing, Ux is constant. And what's gonna be Uy? Uy is greater. It has increased. Uy will be greater, or we can use the word increase. So this is just the basic points required to answer this question. So these are some of the things. And the other point again, we can also consider, I think, let's consider the range, the max, u square sine 2 theta all over 2g. What are the factors that influence the maximum height? Factors in physics, you have to consider the relationship given. The relation or the formula given here, the expression, we have u square, and theta, we also have g. The factors that influence or affect the maximum height, you have to consider the speed of projection. We have to take note of this. Speed of projection instead of angle, let's say speed of projection. This is the first factor. And the second factor again, we also have to consider again the gravity. Simply the acceleration of gravity or simply the acceleration of free fall. The third factor again we need to also consider the angle of projection, speed of projection, angle of projection, and we also need to consider the acceleration of free fall or the acceleration due to gravity. So these are the factors that affect the maximum height. The same way, we can as well do the same thing for the range. U squares sine 2 theta over g. The range again, the factors which affect is the speed, the projection, the angle of projection, and the gravity. So these are the things we need to take note of. So this is just the summary of projection, which is motion under gravity. So just you have gone through this video, please don't forget to subscribe, like, and leave your comments. Thank you.